So with all of those housekeeping items now out of the way, we can begin today's presentation. I'll just ask that we move to slide 2. So to begin today's presentation, we'll first begin by introducing ourselves. I have already introduced myself as the moderator of the session, but for those of you that may have missed it, my name is Candida Chanchi, and I'm the director of the Canadian Nuclear Laboratories Regulatory Program Division. I am joined by my colleagues, Dr. Sun Nguyen, Geoscience Technical Specialist within the Environmental Risk Assessment Division at the CNSC, and Shona Thompson, Senior Project Officer with the Wastes and Decommissioning Division, also at the CNSC. This slide shows the key messages of today's presentation. The following are the points we hope you take away from this webinar session. A disposal facility contains and isolates waste with no intention for retrieval. Its long-term safety after closure must be demonstrated and ensured. A safety case demonstrating long-term safety for disposal facilities must be submitted in support of a license application. It should show multiple lines of evidence that humans and the environment are protected after closure. The CNSC provides rigorous regulatory oversight to ensure that all stages of the development of a disposal facility comply with the safety case, and that the decommissioning and waste management regulatory framework is robust and extensive. In particular, it states that in situ decommissioning is allowed only under exceptional circumstances, such as for legacy sites, under strict safety requirements. In particular, when the end state of in situ decommissioning is a disposal facility, it should be licensed as such and meet stringent requirements for long-term safety. The purpose of today's webinar is to provide a general overview of the long-term safety of disposal facilities and the current in situ decommissioning regulatory framework. We will provide an overview of the regulatory framework for long-term disposal facilities, as well as the regulatory framework for in situ decommissioning. We will also discuss the oversight of radioactive waste management in Canada. We will also discuss how these regulatory policies apply to the proposed near-surface disposal facility and in situ decommissioning, herein referred to as ISD projects. This slide situates us in terms of where we are in the fall webinar series that the CNSC is hosting with respect to the NSDF and ISD projects. As you can see, we have already hosted one webinar on the transportation of radioactive waste, and we still have a series of webinars related to these projects to come. The webinars are designed to present general information on the topics listed, followed by a dialogue and answering questions participants may have on the specific topic covered. Registration is now open for the remaining webinars listed, and we encourage you to sign up. We will circle back to this slide later on in the presentation with more information on upcoming webinars and how to register. We'll begin with project updates on the NSDF and ISD projects. There have been no recent developments or updates on these projects since the last webinar that we recently hosted on October 12th, 2021. Project updates can also be found in the feature articles that are posted on CNSC's website. The summer 2021 feature article for all of these projects can be accessed via the links that we've provided on this slide. I will now turn the presentation over to Shona.
Thank you, Candida. Hopefully everybody can see me. Okay, great. Welcome everyone. My name is Shona Thompson and I am a Senior Project Officer in the Waste and Decommissioning Division here at the CNSC. We will now move on to discussing the regulatory framework with respect to the long-term safety of disposal facilities. To safely regulate an evolving nuclear sector, the CNSC maintains an effective and flexible regulatory framework. The figure on this slide depicts the main elements of the CNSC's nuclear regulatory framework. Specifically for waste management and decommissioning, this framework consists of the Nuclear Safety and Control Act, its associated regulations, specific license conditions to maintain a waste management program, decommissioning plan, and financial guarantee that is acceptable to the Commission. And finally, CNSC regulatory documents and industry standards on waste management and decommissioning. All CNSC regulatory documents are developed to be consistent with national standards as well as international best practices. Some CNSC staff members who developed the reg docs are chairs or core group members in many activities of the National Energy Agency, or NEA, and the International Atomic Energy Agency, or IAEA, on the long-term safety of waste disposal. CNSC conducts independent research and studies to ensure that the most current and up-to-date science and technology are integrated in the regulatory documents. The following regulatory documents focus on waste management and decommissioning. Reg Doc 211, Framework for Radioactive Waste Management and Decommissioning in Canada, version 2, which was published in 2021. Reg Doc 211-1, Waste Management Volume 1, Management of Radioactive Waste, also published in 2021. Reg Doc 211-1, Waste Management Volume 2, Management of Uranium Mine Waste Rock and Mill Tailings, which was published in 2018. Reg Doc 211-1, Waste Management Volume 3, Safety Case for the Disposal of Radioactive Waste, published in 2021. Reg Doc 211-2, Decommissioning, which was also published in 2021. And finally, Reg Doc 331, Financial Guarantees for Decommissioning of Nuclear Facilities and Termination of Licensed Activities, published in 2021. In developing the documents and guidance that fall under its regulatory framework, the CNSC draws upon recommendations of the IAEA, as well as information on best practices from the international and national community. This information includes Canadian Standards Association, or CSA Group standards, which complement CNSC regulatory documents. In the regulation of radioactive waste management and decommissioning, the CNSC makes appropriate use of industry standards created by independent third-party standard-setting organizations, such as the CSA Group. The CSA Group is a not-for-profit organization composed of representatives from the government, industry, and consumer groups, and they currently have one standard specific to decommissioning, which is CSA Group Standard N294-19, Decommissioning of Facilities Containing Nuclear Substances. The following CSA Group standards are relevant to waste management and decommissioning. CSA N292.0, General Principles for the Management of Radioactive Waste and Irradiated Fuel. CSA N292.1, Wet Storage of Irradiated Fuel and Other Radioactive Materials. CSA N292.2, Interim Dry Storage of Irradiated Fuel. CSA N292.3, Management of Low and Intermediate Level Radioactive Waste. CSA N292.5, Guideline for the exemption or clearance from regulatory control of materials that contain or potentially contain nuclear substances. CSA N292.6, Long-term management of radioactive waste and irradiated fuel. CSA N292.8, Characterization of radioactive waste and irradiated fuel. And finally, CSA N294, Decommissioning of facilities containing nuclear substances. Reg Doc 211 outlines 6 principles that govern the CNSC's regulation of radioactive waste and decommissioning. The generation of radioactive waste is minimized. The management of radioactive waste is commensurate with its hazard. The time frame for the assessment of future impacts encompasses the maximum impact. Predicted impacts are no greater than those allowed at the time of the regulatory decision. Mitigation measures are developed, funded, and implemented as soon as reasonably practicable. And transborder effects are not greater than the effects experienced in Canada. We will now move on to discussing decommissioning. And in order to do that, we will begin by defining decommissioning. So what is decommissioning? As stated in Reg Doc 211.2 decommissioning, decommissioning is the administrative and technical actions taken to allow the removal of some or all of the regulatory controls from a facility, location, or site where nuclear substances are managed, used, possessed, or stored. Decommissioning actions are the procedures, processes, and work activities, for example, storage with surveillance, decontamination, dismantling, or cleanup, that are taken to retire a facility, location, or site from service with due regard for the health and safety of people and the environment. The licensee is required to select a decommissioning strategy that will form the basis for planning for decommissioning and facilitate achieving the desired end state of the decommissioning project. When the strategy is to be selected is dependent on the type of license. For Class 1 nuclear facilities and uranium mines and mills, the decommissioning strategy is required to be selected during the siting stage. For Class 2 nuclear facilities, the decommissioning strategy is to be selected during the construction stage. And finally, prior to submitting an application for a license to possess, manage, use, or store nuclear substances at a location, the decommissioning strategy is required to be selected. When selecting a decommissioning strategy, licensees should consider the following options individually or in combination. Immediate decommissioning, also known as prompt decommissioning, deferred decommissioning, and in situ decommissioning. Immediate decommissioning is to decontaminate, dismantle, and/or clean up without any planned delays. Deferred decommissioning is to place the facility in a period of storage with surveillance, followed by decontamination, dismantling, and/or cleanup, or to conduct activities directed at placing certain buildings or facilities in a safe and secure interim end state, followed by a period of storage with surveillance, and ultimately decontamination, dismantling, and/or cleanup. In situ decommissioning is to place the facility or portions thereof in a safe and secure condition in which some or all of the radioactive contaminants are disposed of in place, which may result in the creation of a waste disposal site. The CNSC does not impose a preferred strategy, provided the regulatory criteria are met. Furthermore, the CNSC does not guarantee acceptance of any of the options selected, as they must meet the regulatory criteria to ensure safety for the life cycle of the project, no matter which option is selected. In addition, justification of whichever strategy selected is required and should include a comparison of alternative decommissioning strategies and a comparison of the relative advantages and disadvantages of the remaining strategies in a systematic and traceable fashion. Consultation with stakeholders, both Indigenous and the general public, is critical to ensuring transparency in the selection process and throughout the entire regulatory process and project lifecycle. The Canadian context for in situ decommissioning is complex and has recently been updated to reflect the fact that nuclear facilities in Canada span the entirety of the fuel cycle, from uranium mining to waste disposal. Canada's regulatory framework around in situ decommissioning and waste must reflect this. As part of the recent revision of Reg Doc 211.2 decommissioning, further requirements and guidance around the conditions for which in situ decommissioning could be considered not a reasonable decommissioning option for situations where removal is practicable, not acceptable for commercial MPPs, and not to be considered for new nuclear facilities with the exception of uranium mines and mills. In situ decommissioning is only to be considered under specific circumstances. These include exceptional circumstances, such as following a severe accident, where dismantling poses a risk to workers, the public, and the environment. The other case for in situ decommissioning is for legacy sites, where decommissioning was not planned during the design phase. In some cases, legacy facilities that in situ decommissioning could be considered an option for will result in the creation of a waste disposal facility. In this case, the safety of the facility must be demonstrated through a safety case that meets the Canadian requirements for a disposal facility and must remain under institutional control for the foreseeable future. It is critical that legacy sites be defined in the Canadian context to provide clear delineation of which facilities do and do not fall into this classification. Legacy sites are defined as research and demonstration facilities or facilities dating back to the birth of nuclear technologies in Canada, for which decommissioning was not planned as part of design. If a facility falls into this definition, they could consider decommissioning through in situ decommissioning, but that does not guarantee acceptance of this option. Legacy sites are defined in both Reg Doc 211.2 and CSA N294. Next slide, please. Could I get the next slide, please?
Just a second, Shona, our person in the background is having technical issues, so just bear with us for 1 minute, participants. Sorry, folks, we're just trying to get somebody else that can bring the presentation up on the screen. Thanks, Leanna. Can you go to the next slide? Perfect.
Great, thank you. A technology fail on my final slide. Financial guarantees. They are required as part of license applications and approved by the Commission. They are payable to the CNSC. They are separate from a licensee's assets and can be accessed by the CNSC if required. They are required throughout the entire life cycle of a nuclear facility other than release from licensing. They are to be updated and reviewed every 5 years or sooner if requested by the Commission. And they're also subject to annual reporting to demonstrate value and validity. Next slide, please. We will now move on to discussing how the long-term safety of waste disposal facilities are ensured. For this, I will pass the presentation over to Son. Thank you.
Thank you, Shona. Welcome, everyone. My name is Sen Nguyen, and I am a geoscience technical specialist with the Environmental Risk Assessment Division here at the CNSC. A disposal facility is one where waste is managed without the intention to retrieve or relocate the waste. This differs from a storage facility where the waste can be retrieved or moved. A CNSC license is required for each stage of the disposal facility life cycle, from the construction, operation, closure, or decommissioning, as well as post-closure. During these stages, the license will require renewal at set intervals as well. This would involve a license renewal hearing in front of the Commission. Disposal facilities must isolate and contain the waste for the long term. Following operations and closure, the facility enters the post-closure stage, which includes the institutional control period, which is typically hundreds of years long. The post-closure stage as a whole can last for hundreds to millions of years, depending on the types of waste. The long-term safety of a disposal facility is determined with the protection of human health and protection of the environment at the forefront. Applicants must demonstrate to the CNSC how the disposal facility will remain safe during the period of institutional control, as well as for the long-term post-closure period. Long-term safety of a disposal facility must rely on passive means of control. Passive safety, which is a CNSC requirement for disposal facilities, requires that barriers be able to isolate and contain the waste with minimal need for human intervention, such as treatment of contaminated waters. Next. This slide lists some of the fundamental requirements for ensuring that the long-term safety of disposal facilities is achieved. First and foremost, it is vital that the waste remain contained and isolated during the time that it remains hazardous. Containment and isolation are achieved by a multiple barrier system with both engineered man-made components and natural components, such as the underlying bedrock and other geological units. The barriers must also have multiple safety functions that are independent of one another and complementary, such that they cannot fail through a single failure mode. The overall barrier system must be robust and rugged enough to withstand and resist disruptive events expected during the assessment timeframe. Examples of events are earthquakes, floods, as well as other natural and human-induced events. The proponent licensee must develop a robust safety case to demonstrate both pre-closure and post-closure safety of a disposal facility in support of license application. The safety case synthesizes all the multiple lines of evidence showing the facility can protect human health and the environment for the assessment time frame. Next slide, please. The CNSC's role evolves during the life cycle of a disposal facility. When the license application and supporting documentation are received, they are reviewed by CNSC technical experts, many of whom have advanced degrees through the science-based, risk-informed technical assessment process. Technical assessment demand rigorous engineering and scientific analysis, taking into consideration the CNSC's experience and knowledge of best practices. CNSC staff assess the documents against regulations, regulatory documents, international guidance, Canadian Standards Association, professional judgment, and knowledge gained through independent regulatory research. If CNSC staff conclude that an application is not complete or satisfactory, the proponents will be asked to submit additional information and/or revise the documents to reflect changes to address CNSC staff comments. The revised document is then reviewed once again by CNSC staff. This process continues until staff are satisfied all requirements are met. Normally, applications do not proceed to a decision until staff are satisfied that the application contains all of the relevant information needed for the Commission to make a licensing decision and that all regulatory requirements have been met. In addition, CNSC staff maintain frequent dialogue with proponents and other stakeholders, for example, with public outreach activities, to clarify expectations and requirements on long-term safety. CNSC staff conduct independent verification calculation of mathematical models. CNSC staff also publish and disseminate research results on long-term safety in journal papers, conferences, and presentation. If the Commission grants a license to a facility, the CNSC's role expands to include compliance. Next slide, please. We will now move on and discuss the safety case, which is the main supporting documentation that demonstrates the long-term safety of a disposal facility. In accordance with Reg Doc 211.1 Volume 3, the safety of a disposal facility must be demonstrated in the pre-closure and the post-closure phases. This demonstration is performed with a safety case. The safety case is a documented set of multiple lines of reasoning and evidence that must demonstrate how the health and safety of workers, the protection of the public health, as well as the protection of the environment are ensured at all times. Uncertainties associated with the long-term safety of a disposal facility will increase with the hazardous life of the waste. The waste with the longest hazardous life would be spent nuclear fuel, and as such, it would harbor the most uncertainty as the waste remains hazardous for millions of years. The waste with the shortest hazardous life, low-level waste, would have the lowest levels of uncertainty as the waste will typically remain hazardous for hundreds of years. The level of rigor and scrutiny in developing and assessing the proponent's safety case is commensurate with the nature of the disposed waste. This is referred to as a graded approach. Next slide, please. The safety case is a living document that must be updated for each licensing stage. A monitoring and verification program is implemented by the licensee throughout all the phases to collect data to confirm that the facility performs as expected from the most updated safety case. The data from the monitoring verification program, as well as from research and development, experience during construction and operation, are all used to update the safety case. CNSC staff continually review the results of the monitoring verification program in order to ensure that all phases of the development of the disposal facility are as expected in the safety case. Next slide, please. This graphic illustrates commonly used classes of arguments included in a safety case. These arguments relate to the properties of the waste, to the site characteristics, to the engineering design developed using the best available science and technology, to the long-term safety assessment, as well as to any complementary arguments such as natural analogues. These arguments together demonstrate, using multiple lines of evidence, that the multiple barrier system can provide long-term containment and isolation of the waste, which in turn ensure the protection of the public and the environment. Let's talk first about the first class of arguments related to the waste characteristics. In Canada, waste is classified according to the following 4 classes: low-level waste, intermediate-level waste, high-level waste, and uranium mine and mill tailings. The classification of waste is directly associated with its hazard level and half-life. The waste classification is an important component of the safety case, as the optimal method and depth of the disposal facility required to ensure safety will depend on the class of waste and the characteristics of the waste, in particular, how long the waste remains hazardous. The safety case must clearly define the characteristics and hazards for the waste to be disposed. The specific characteristics of the waste are used to justify the chosen disposal method, timeframe, and depth. As an example, only low-level waste would be permitted to be disposed of in a near-surface disposal facility. In this slide, we show an example of the hazardous lifetime for the NSDF waste as compared to nearby natural sources of radioactivity and background. The radioactivity decays relatively rapidly in the first 100 years due to the decay of shorter-lived isotopes, such as cesium-137, and decays to lower than near-surface ore bodies decades after closure. The NSDF facility is designed with a multiple barrier system to contain and isolate the waste for at least 550 years that encompasses the hazardous life of the waste. In this slide, we show another example of the hazardous lifetime of the waste for the NPD closure project and the isotopes that are principal sources of the activity. Once again, this hazardous lifetime could be compared to other nearby natural sources of radioactivity and background. In the case of NPD, the majority of the radioactive inventory is in the reactor vault, located underneath the bedrock. For NPD, the radioactivity decays to lower than near-surface ore bodies hundreds of years after closure. The site where the facility is proposed to be located must be characterized by field investigation on the geology, seismicity, hydrogeology, geomorphology, and biosphere characteristics of the site, as these features are often part of the natural barrier system, and it is crucial that background information be obtained. The past history, present state, and future evolution must be evaluated using evidence obtained from the site characterization. The above information will allow for a credible demonstration that the site is compatible with the facility. First of all, this data should demonstrate that the site's future evolution would not adversely affect the safety functions of the multiple barrier system and its components. Secondly, the site would play a significant role in the overall safety of the disposal system. For example, the geosphere can play a significant role in providing containment and isolation of the waste, in addition to the engineered barriers, such as through low hydraulic conductivity, which leads to slow groundwater movement. Therefore, the role of the geosphere as a natural barrier must be defined and assessed. For low-level waste, Canadian and international guidance both suggest near-surface disposal as an appropriate method. For example, the main component of the NSDF barrier system proposed by CNL would be an engineered containment mound. The multiple barrier system of the engineered containment mound consists of a multi-layer cover system that limits water infiltration into the waste and to limit intrusion, a multiple layer base liner that limits water that has come in contact with the waste to infiltrate into the subsurface, the natural subsurface that retards the movements of contaminants, and a perimeter berm that physically contains the waste. The ECM, the engineered containment mound, is engineered to resist severe disruptive events, such as a 1 in a 10,000 years earthquakes. Next one, please. For the NPD, after decommissioning, the main source of radioactivity is located in the reactor vault and is associated with the metal reactor components, such as pressure tubes, that would be left in place. Again, radionuclide migration from the source would be limited by a multiple barrier system. The reactor components are barriers themselves, since they are made with corrosion-resistant metals, such as zircaloy and stainless steel. The radionuclides can only leach out to the pore water of the grout when these metals corrode. This happens at a very slow rate. All the underground openings will be crowded with a grout mixture having low permeability, resulting in slow groundwater movement. The other successive barriers are the concrete walls and floors around the reactor vault and building, then the bedrock, and finally a multi-layer concrete cap and earth liner system. The multiple barrier system is designed to resist strong disruptive events, such as a 1 in 50,000 years earthquake. Next slide, please. Central to the safety case is the long-term safety assessment. The safety assessment is a systematic evaluation of the potential impact of the disposal facility on humans and the environment. In the safety assessment, quantitative estimates of this impact are performed with mathematical models. These models simulate the degradation of barriers, the transport of radionuclides, and their uptake by people and in the environment over the long periods of time being assessed, such as tens of thousands of years. The results, usually in the form of a dose to people, must meet stringent acceptance criteria. For example, the typical acceptance criterion for public dose is 0.3 millisievert per year, which is more than 6 times lower than background dose in Canada at 2 millisieverts per year. Using a dose criterion that is lower than the dose limit of 1 millisievert per year allows for uncertainty to exist in model predictions and remain below criteria. Next slide, please. Mathematical models used in quantitative assessment are simplified representation of reality and represent long time periods. Therefore, the results are subject to uncertainty. Steps can be taken to reduce this uncertainty and improve confidence in the results. Specifically, confidence must be provided that the models provide bounding impact estimates, meaning that there is a good chance that the models are over-predicting the impact and still meet acceptance criteria. This is done by software, quality assurance, quality control, that includes verification, calibration, and validation of the computer models, deliberately using conservative, pessimistic assumptions and data needed for the impact calculations, and using multiple models to achieve comparable results. Defining multiple evolution scenarios for the disposal system. And lastly, using in situ site data, natural analogs, and past geological information in order to validate parts of the models. Next slide, please. This slide presents an example of some of the results of the post-closure safety assessment performed by CNL for the proposed NSDF. The slide shows the maximum dose for a hypothetical family with a house and vegetable garden on top of the ECM and raising cattle around it. In particular, the family uses the Ottawa River as their source of drinking water. Many scenarios are considered in the safety assessment. The normal evolution scenario is the one which is considered most likely. The maximum calculated dose for the normal evolution scenario is much smaller than the acceptance criterion. Other very conservative scenarios, such as total mass excavation, where all the waste and the ECM are excavated out and spread over the surface, are also considered. Even for this very conservative scenario, the results are more than twice below the acceptance criterion. Next slide, please. The other class of arguments in the safety case can come from natural analogs. Natural analogs are examples found in nature that have features that are similar to a disposal system or some of its components. For example, the Cigar Lake ore body is one example of natural analog for deep geological disposal. At Cigar Lake, very high-grade ore was formed billions of years ago and is analogous to a disposed waste. The clay halo around the ore is analogous to low permeability engineered barrier. Radionuclides move very slowly through the halo before it reaches the overlying sandstone. At the surface, however, no radionuclides at the present time have been found or detected. Another example is the burial mounds, which were built hundreds to thousands of years ago in North America, and they are natural analogs to the NSDF and provide direct evidence that human-made mounds can survive thousands of years. Some of these mounds are still in good condition, although they were not built according to present engineering design and standards. For example, the Monk's Mound in Illinois, USA was built around 955 common air. It is located in an area with comparable precipitation and seismicity as the NSDF. It is still in excellent structural conditions and demonstrate the longevity of the mound under similar environmental conditions to the one at the NSDF. I will now pass the presentation back to Candida.
Thank you, Sun. Further information on each of our upcoming webinars with respect to the NSDF and in situ decommissioning projects is found on this slide. Registration is available through the CNSC main webpage, but for ease of reference, we've also included the registration link on the bottom of this slide. And we really hope to see you all there in our upcoming webinars as well. This concludes our presentation.